In this video, we're going to look at the examples from Chapter 6 in Business Finance. In the first two examples, we don't have any calculations. We're just going to talk through these questions and talk about what the answers are them. So first we have, is the yield to maturity on a bond the same thing as the required return? Well, if we remember from the PowerPoint lecture and the chapter reading, yes, they are the same thing. So yield to maturity is the required rate of return within the market. It is not the same thing as the coupon rate. The coupon rate is the stated interest rate of the bond, and the yield to maturity is the rate of return within the market. So if we have a 10% coupon bond that sells at par, when a bond sells at par, that means that the coupon rate and the yield to maturity are exactly the same. So at the date of issue, both the yield to maturity and the coupon rate are 10%. 2 years from now, the required rate on the same bond is 8%. What is the coupon rate on the bond now, 2 years later, when the required rate is 8%? The coupon rate does not change on a bond, except for very specific bonds, which we talked about in the lecture, which are the floatable rate bonds. That's the only kind of bonds that has a changing rate. Otherwise, the coupon rate is a rate that is constant throughout the entire life of the bond. The yield to maturity, or the market rate, does change throughout the life of the bond because it changes based on the current market. So at 2 years later, the coupon rate is still 10% and the yield to maturity is now 8%. What happens if we buy a 7% coupon 20-year bond when it's first issues? So that means we bought a 20-year bond with a 7% coupon rate or interest rate on the coupon payments. If interest rates suddenly rise to 15%, what will happen to the value of our bond? Well, the value of our bond will decrease, and that is because the value of the bond is inverse to the interest rate relationship. And this is because if we have a 7% bond and the market rate is 6%, that means that we are earning a greater return than the market, which increases the value of our bond because investors can get more from our interest than they can in interest within the market. Well, the exact opposite happens when the market rate is higher than the coupon rate. So when the market rate is higher than the coupon rate, that means I can get a better interest in the market from my investment than I can from investing in a bond, which decreases the value of that bond. In example 3, we're going to calculate the price of a bond. So if you remember from Chapter 6 and the Chapter 6 PowerPoint lecture, we introduced price and yield as new Excel formulas within this chapter. So in this formula, we're trying to calculate what the current bond price is. So we have a 7% bond. It has 13 years left to maturity. And the bonds make annual payments, so it's one-time payment, or coupons, and it has a par value of 1,000. If the yield to maturity on these bonds is 8.4%, what is the current bond price? So we put all of that information into Excel. For the settlement date and the maturity date, we can use any dates as long as they are 13 years apart. Excel doesn't care about it being a specific date. When Excel does the calculations, it does the calculation for the span of time. So as long as whatever date you put in the settlement date and whatever date you put in the maturity date are the length of the bond to maturity, Excel will do the calculations for you. So the value for this formula is the price function. So we're using the price function within Excel. You can see that this returns the price per $100 face value of a security that pays periodic interest. So it's going to give us the price of a bond per $100 of face value. And we're going to do a calculation, so it just tells us what the current bond price of the bond is. So we put our parentheses, and then Excel tells us what order we need to take information in. So first is the settlement date. Put a comma, and now we want the maturity date. Then the rate, that is our coupon rate on the bond. Next, this YLD stands for yield. That is our yield to maturity calculation. The redemption is our face value as a percent of the par value. So this is our 100% face value as a percent of par. The next thing it wants is the frequency. So much like when we were doing the time value of money calculations in Chapter 5, and we had a choice for ordinary annuity or annuity due, we have a choice for frequency. So we have 1, 2, or 4. So I'm going to put in 1 for an annual. And then the basis, which is the number of days in a year, and we're just going to default to 0. 0 is the default basis, and that's what we're going to calculate for this. Now, because this returns the price per $100 in par value, and we just want a straight price, we're going to divide this by 100 times our par value. And that tells us that the current price of this bond is $891.74. This would be a discount bond. It is trading currently for less than the par value. In this next example, we're going to use the yield formula. So that was the second formula that was introduced in Chapter 6 in Excel. So that is, we type in yield, and we're going to get the yield to maturity for this bond. So when we're calculating that, we take each of the items as they are presented. So first, the settlement date, then the maturity date. Next is our rate, or our coupon rate. The PR stands for price. So that is our bond price, our current bond price. Redemption is the face value of the bond, or the percent of par. The frequency is 1 for an annual coupon per year, 1 payment. And then our basis is 0, which is the default. So the yield to maturity on this bond is 6.42%. In this example, we have the years to maturity, the coupons are annual, we have the bond price, the face value, and the yield to maturity, and what we're trying to figure out is what the bond's coupon rate is. The first thing that we have to do that is calculate the coupon payment. So we use the payment formula, and we used that before in Chapter 4 and Chapter 2. So we have our rate. So we're going to get used to, when we're doing the payment for bonds, to calculate in how many times that rate occurs. So if this was a semi-annual bond, we would have to take that rate and divide it by 2. So we're just going to go ahead and be in that habit, and we're going to take our rate of 6.14 and divide it by the number of coupons per year, or 1. The number of periods, so we have 12 years until maturity and 1 coupon per year for an annual payment. So we're going to take the years to maturity times the number of coupon payments. Next, we have the present value of the bond, and the present value is the current bond price. Oh, I need to put a comma in before that. In class, I accidentally used all dividing instead of all commas, and of course broke my formula. So we have our bond price is the present value, and the face value is the yield to maturity. I'm going to make the bond price, or the present value, negative, because remember, if one's positive, one has to be negative. And then 0, which is the default for an ordinary annuity. That gives us a coupon payment of $65.01. Well, we know that the face value or par value of a stock times the coupon rate equals the coupon payment. So if we rearrange that formula and take the coupon payment divided by the face value, that will give us the coupon rate. So coupon payment divided by the face value, and that gives us the coupon rate of $6.50. The next 3 examples use the Fisher effect formula from class, and the Fisher effect formula is 1 plus R, or the nominal rate of return. R, capital R is the nominal rate of return, equals 1 plus little r, which is the real rate of interest, times 1 plus h, which is the inflation rate. The value for the approximate real rate of interest is that r equals r plus h. So in this formula, we have 4.7, which is our large R, or our nominal rate of interest, and we have h, the inflation rate. So if we're trying to solve for the real rate of interest, then we need to, for the approximate, rearrange our equation. By subtracting h from both sides of the equation, we get an equation that is R equals capital R minus h, or that the real rate, the approximate real rate, equals the treasury rate minus the inflation rate. For the exact value, we need to rearrange our equation. So we're trying to get 1 plus r. This means we need to divide each side of our formula by 1 plus h, and then subtract 1. So the new formula that we're looking at is h equals 1 plus capital R, or our nominal rate, divided by 1 plus the real rate. Oh, that's solving for interest. But divided by 1 plus the interest rate minus 1, or the inflation rate minus 1. So we have 1 plus the nominal rate, or treasury rate, divided by 1 plus the inflation rate minus 1, gives us the exact rate. I'm going to copy these into our next example, which also uses the same formulas, except we're going to rearrange them. So now we have the treasury rate, or the real rate. And we have the real rate and the inflation rate, and we're trying to get the treasury rate. So then our formula is we're trying to get the real rate equals 1, or the nominal rate, 1 plus the real rate times 1 plus inflation minus 1. So if we rearrange to get the nominal rate by itself, so the treasury rate or the nominal rate equals 1 plus the real rate times 1 plus inflation minus 1. And let's copy that again into the next one. Now we are solving for the inflation rate, or H. So we need to take each side divided by 1 plus R to isolate H by itself. Then we get 1 plus the nominal rate divided by 1 plus the real rate minus 1. So to calculate the inflation rate, or H, using the Fisher effect, we take 1 plus our nominal rate divided by 1 plus the real rate minus 1. And that gives us an inflation rate of 2.75%.